Okay, so let's look at some examples of how we might use this. Based on past experience, a bank believes that 7% of the people who receive loans will not make payments on time. The bank recently approved 200 loans. Okay, so we got 200 loans, and they think 7% are going to default on it. What would be the mean and standard deviation of this given this information? Well, I would expect 7% to default, and then using our sample proportion formulas, it's 0.07 times 0.93 divided by 200, then take the square root of that. Uh, are the assumptions met that we can use these formulas and suggest what they're saying? Well, NP is 200, N is our sample size is 200, and our probability of success is 0.07. So if I do N times P, I get 14, and then N times 1 minus P, that gives us 186. So our N is definitely large enough to assume a normal model and that these formulas are accurate. And then the other condition is we have to kind of think about independence, and there isn't necessarily a formula for this. I'm sorry, I'm misreading this question. What is the probability that more than 10% will not make payments on time? So if I expect 7, what's the probability that over 10 would default on their loans? Well, this is a normal model. This is a normal CDF. And so we would just type that in the calculator of having a lower, let's see, let me just kind of show you the calculator formula. So we have our lower bound is 0.1, our upper bound would be infinity, or we'd use just the 1e to the 99. The probability of success is 0.07, and then the standard deviation that we calculated, and we get that the probability of that statement happening would be about 4.8% of the time. So a lot of percents being thrown around here. So let me make sure we understand what this is saying. If I expect 7% of the population to default on their loan, and I'm curious what percent would be higher than 10. So I show up to work and my boss says, okay, but if it's 10%, we're going to lose money. So should I be freaking out or not? And I go do this calculation. I come back, well, we would see something higher than 10% only 4.8% of the time. So then my boss would calm down and be like, okay, so it's very rare that we would have more than 10% default. All right, different question. Suppose one student tossed a coin 200 times and found only 42% heads. What was the coin made weird? Is that odd that that head showed up 42%? And then find the probability that that particular situation would happen. So let's start with assumptions. And we have a sample size of 200. I expect the coin to be heads 50% of the time. So the 42% would be our sample percent, but what do I expect out of a coin? And that would be 0.5. And so when I do NP, N times 1 minus P, the sample size is large enough. So I can go ahead and use normal models and calculate p-values on this. So then I need to figure out what the standard deviation is and what the sample proportion is. Well, the sample proportion is going to match our 42%, so that's 0.42. And then I just need to figure out what the standard deviation is. Well, standard deviation I expect it to be 0.5. Even though I got 0.42, that's what I'm kind of comparing this against, but I expect it to be 0.5. So let me kind of show you how we'd calculate this. So we're looking at a norm CDF, and I'm going from negative infinity up till 0.42 because I'm trying to figure out what's the likelihood that it could be 42% or less, given that I expect it to be 0.5%? So in your norm CDF, it's negative infinity up to 0.42. This probability of success is 0.5. And then our standard deviation is given by the square root of 0.5 times 0.5. Okay, so I just want to go back and clarify. When we do standard deviation, that's based on what do we expect to see in the problem, not based on what I saw. It's before, in other words, before we flipped any coins, I expected it to be 0.5. So that's why a standard deviation would be based off of that. And so when we calculate the probability from the CDF, we get a p-value or probability of 0.018, and that's about 1%. So, do I believe the student? He says, yeah, I was flipping coin and I flipped it 200 times and I got heads 42% of the time. You would look at him funny and go, no, you didn't. You miscounted. You're dishonest. There's some sort of issue is really at hand. All right, last question then. Assume 30% of the students at school wear contacts in a sample of 100. What's the probability that more than 35% of them will wear contacts? Okay, well, let's talk about our assumptions for a second. Do we have a large enough sample size? So that'd be 100 times 0.3 and 100 times 0.7, which does work out just fine. What about mean and standard deviation? So I'm kind of getting ahead here. The mean would be 0.3. That's what I expect to see is 30%. The standard deviation is the square root of 0.3 times 0.7 divided by 100. So we get that number there. Assumptions are fine. We have a large enough sample. So I can go ahead and use a normal model to approximate our probability. So when we do norm CDF, I want its probability that's more than 35%. So we're looking at the upper part of the normal curve. So that's 0.35 to out to infinity, which is that's what we're using for infinity, is this number here. Probability of success is 0.3. That's the standard deviation we calculated. And so the likelihood of this happening would be about 13-14% of the time. Again, a lot of probabilities being thrown around in this problem, so let me make sure we get this. If I think it's 30% and someone comes up to me and says, well, no, I think it's 35%. Well, I'm going to go collect some data and I'm going to try to show them that I'm right and they're wrong. I would, the likelihood of it being bigger than 35 or 35 or more is only going to happen 13% of the time. While that's not huge, that is enough to kind of stop and go, it could happen. I could try to gather the information, and we still could find out that it is larger than 35%. So anyways, that probability being about 14% there. So